There seems to be a good deal of confusion when it comes to the terms response time and integration time of energy sensors. In this video, we'll clarify the meaning of these terms as they apply to Ophir's pyroelectric smart sensors used for measuring laser pulse energies. A pyroelectric sensor is based on a pyroelectric crystal. When a laser pulse is absorbed by the sensor's absorber, it's turned into a heat pulse in the crystal, and thanks to the physical properties of pyroelectric crystals, the crystal then generates an electric charge proportional to the heat that was absorbed, meaning proportional to the energy that was in the laser pulse. The two surfaces of the crystal are metal coated, so the coated crystal in effect becomes a capacitor. The total charge generated is collected and becomes a voltage pulse, which then gets measured. The response time of the pyroelectric sensor, not to be confused with integration time, we'll get to that shortly, depends on the time it takes for the heat to enter the crystal and heat it up. For Ophir's metallic type pyrosensors, so-called because the metallic coating on the crystal, the one that turns the crystal into a capacitor, serves as it is as the sensor's absorber surface, this response time is on the order of microseconds, and thus the metallic type can run at high repetition rates. For pyroelectric sensors having a broadband absorber coating on top of the metallic coating, such as Ophir's BF and BB black coated types, the response time is on the order of milliseconds with a correspondingly lower repetition rate. The integration time is something else. It's the time during which we hold the voltage signal as it maximizes and stabilizes so that we can measure it. At the end of the integration time, we reset the voltage back down to zero so the sensor is ready for the next pulse. The time it takes for this reset depends on the thermal relaxation time of the sensor and on the RC time constant of the electronics. In other words, the integration time is the time window during which a given pulse is measured. This explains, it should be noted, why choosing a given maximum pulse width setting determines the maximum pulse repetition rate, as can be seen in the specifications. When the user sets the maximum pulse width, for example 2 milliseconds, this automatically determines the integration time. Even if the laser's pulse width is actually only 3 nanoseconds, the sensor will hold the voltage for 2 milliseconds in this example and integrate it, meaning collect and measure it. If the laser pulse is actually longer than, for example, 2 milliseconds, yet one sets the maximum pulse width to the 2 millisecond setting, some of the pulse will be cut off and ignored, resulting, of course, in an incorrect reading. If, on the other hand, the maximum pulse width setting is set to much longer than the actual laser pulse width, that's going to allow some extra noise to get in. In general, one should choose the shortest maximum pulse width setting that's still definitely longer than the actual laser pulse.